We're going to talk about logarithmic functions and their graphs, and this is learning target 7D. By the end of this lesson, you will be able to explain the connection between an exponential and log function from a graph perspective. We will also talk about identifying all transformations for a logarithmic function, including any asymptotes, as well as describing what the graph would look like using the domain and the range. So the first thing I want us to recall comes from our last learning target, which was learning target 7C, and that was what the definition of a log function is. So a logarithm base b of a positive number x satisfies the following definition. If our base is bigger than 0 but not equal to 1, then log base b of x is equal to y is equivalent to b to the y equals x. What this told us in our last section was that exponential functions and log functions are inverses. And in our last unit, we learned all about inverse functions and how inverse functions flip-flop the x and the y values, or flip-flop the input and the output, so our domain and our range are changing on the graphs. Let's look at two graphs side by side. On the left side here, we have an example of an exponential growth graph of y equals 2 to the x. As we can see, it's growing over time, and we have that horizontal asymptote here at y equals 0. Now, if we were to create the inverse to this graph, that would be our y equals log base 2 of x graph. Couple ways to get the inverse. It is the reflection over the line y equals x, or we could use the paper trick that we talked about during class in our last unit. And on the right side over here is a sketch of our log graph. Let's talk about a few key things. The first is where the asymptote got moved to. So on an exponential function, we had a horizontal asymptote, which when that horizontal asymptote is inverted, we end up with a vertical asymptote at x equals 0 now. The other thing I want us to pay attention to is this one point on our graph. We have 0, 1 as a point on our exponential growth graph. When we invert that, we're flipping the x and the y values, so 0, 1 would go to 1, 0. That's just one example of one of these points moving. Every single point on an exponential graph flips the x and the y values to get all of these points on our log graph here. Couple key differences. So in an exponential function, our domain was all real numbers, because on our graph here on the left side, it keeps going to both the left and the right, and we're able to sub in positive numbers, negative numbers, as well as 0. Our range, however, was restricted to be y is strictly greater than 0, because we just had everything above our horizontal asymptote. And we also had that horizontal asymptote at y equals 0. Well, when we invert that and get a log function, remember our domain and our range flip-flop. So our domain for our exponential function becomes our range for our log function, and our range for our exponential function becomes the domain of our log function. And we can see this in the graph here. In a log function, we just have a domain of x being strictly greater than 0. And on the graph, that's represented because nothing passes that vertical asymptote. There are no x values or y values or points even over here on the left side of the vertical asymptote. This is actually in the definition of a log function as well. So at the beginning, we said that the logarithm base b of a positive number x satisfies the following definition. The reason that that has to be a positive number x is because the domain of a log function is strictly positive values. Notice we have no equals to bar here because we can't actually touch or cross that vertical asymptote on our graph. So our domain is strictly x is greater than 0. Our range, on the other hand, is all real numbers now. Because this graph continues moving up, it does slowly increase over time, and then it goes down towards negative infinity as well. So our range is taking up all of those positive, negative, and the value 0 on our y-axis. And as we talked about before, our horizontal asymptote, when that is inverted, becomes our vertical asymptote, which is now at x equals 0. Since we have both of these graphs now that we'll be answering questions on, we want to make sure that our asymptotes have that full equation. So for a horizontal asymptote, that would be y equals our number, and for a vertical asymptote, we want to make sure that that's x equals to represent the vertical line there. Now, one thing you might be wondering is, well, what about an exponential decay graph? Well, we can invert that as well. Here we have an example of y equals 1/2 to the x. So our base here is less than 1, so this is an exponential decay, and we would invert it the same way. We get a slightly different graph than we did up above. For our log graph up above, it's growing over time, and for our log graph down below, this is actually decreasing over time because it came from an exponential decay graph. But we still have that same vertical asymptote at x equals 0. We have a domain here that x is strictly greater than 0, and our range values are all real numbers. Let's look at how these transformations are going to affect our graphs. So just like we had for our exponential functions, we're going to use the same transformations for our log functions. Now our parent function here, we have lots of different options depending on what our base is. So in general, it would be y equals log base b of x, and we would want to know specifically what that value for b is. But notice we have nothing multiplied to the log, we have nothing added, subtracted to the x, or added, subtracted outside, and we have no negative signs anywhere on our parent function. Now our 4 transformations are the same transformations we've been talking about all year. We first have our horizontal shifts, so that would shift the graph right or left. That happens inside the function, so for a right h units, that would be x minus h. For left h units, that would be x plus h. Our second transformation is our vertical stretches and compresses. That's what happens when we multiply our log by a number out front. If the absolute value of that number is bigger than 1, we have a stretch. If the absolute value of what we're multiplying the log by is less than 1, but still bigger than 0, then that is what we call a compress. Now, if that a value is also negative, that brings us to our first reflection. So if we have a negative sign multiplied to the log, that would be a reflection over the x-axis. And if we have a negative sign inside the log, that would be a reflection over the y-axis. And our last transformation is our vertical shifts. So if we add a number outside of the log, we're moving it up k. And if we subtract a number outside of a log, we're moving it down k. Now, just like all of our other parent functions, the domain and the range are going to change according to the transformations that are applied. So as a review from up above, our domain starts off with x is greater than 0. Because in that standard log graph that we had this graph, let's assume it came from an exponential growth, then it's slowly growing over time, and we have that vertical asymptote right here at x equals 0. So our domain starts off with x being strictly greater than 0, and our range is starting off with all real numbers. Now the nice one here is the range. No matter what transformations I do, if I started off with a range of all real numbers, no matter what I do to stretch, flip this, shift it left, right, up, or down, or do any reflections, our range will still stay as all real numbers because it started off as all real numbers. However, the domain is now going to be the piece that changes. And what's going to change this are 2 of our transformations. The first is the horizontal shifts. So if I take this graph and I shift it to the left or to the right, then the graph as well as the vertical asymptote are going to shift according to however many units we're moving to the left or moving to the right. So horizontal shifts are going to change the number in our domain inequality. Vertical stretches or compresses will not change our domain because those are dealing with our y values. Same thing with a reflection over the x-axis, that's changing our y values as well. But a reflection over the y-axis is going to change the inequality for our domain. So if we flip this graph over the y-axis, we're going to get a graph over here that's now decreasing down to the right, and everything is to the left of the vertical asymptote versus being to the right. When this happens, our domain now is x is being less than 0 since it's on the left side of our vertical asymptote. So a reflection over the y-axis then is changing the inequality sign for our domain. If we have both a horizontal shift and a reflection over the y-axis, then we would have both the inequality change as well as the number that we're being compared to in the domain. So if we shift one direction and reflect it, we'll have both parts of that domain that will change. Now we've already hinted at it, but the vertical asymptote will change as well, and that vertical asymptote is going to depend on those horizontal shifts. because if I'm starting off at x equals 0, I can think about it as if I were to put a pencil vertically down on my paper at x equals 0. If I take this pencil and I shift it to the left or to the right, then that's going to change the equation of our vertical asymptote. So what that means overall is that the vertical asymptote depends on what horizontal shifts we have, or if we have no horizontal shifts, then our vertical asymptote will stay at x equals 0. And the vertical asymptote and the domain do go hand in hand now, since that vertical asymptote is the boundary for our domain. Let's look at some examples. So these examples are going to be similar to what we did when we graphed exponential functions. We're going to find the parent function, the transformations. We want to find the equation for the vertical asymptote. We want to also find the domain and the range, and we're going to use this information to sketch a graph. I do notice I have one typo in here. This should say, using the information, sketch a graph of the function including the vertical asymptote, since we now have a log function. So make sure you change that in your notes. So let's look at our first example. We have y equals log base 2 of x minus 3 plus 5. Why don't you guys pause the video here and list out what our parent function is. So our parent function for this one will be y equals log base 2 of x. So in general, any parent function is going to be log base b of just x, so we just need to identify what the base is. So in example 2 here, in example 1, our base here is 2. How many transformations do we have in this first example? So in this example, we have 2 transformations. Why don't you guys pause the video and list both of those transformations? So our first transformation we have is we're shifting to the right 3. That's coming from the x minus 3. And our second transformation is up 5, which is coming from the plus 5 outside of the log. From here, we can now determine our vertical asymptote, the domain, and the range. Since we have a vertical asymptote, I know that that equation has to be x equals, since we now have a vertical line. Well, this vertical asymptote started at x equals 0, and what's going to shift it is any horizontal shifts. So by going to the right 3, we're taking x equals 0 and shifting it 3 units to the right, so we'll end up at x equals 3. If we were to sketch this out on a graph, I can just start with my vertical asymptote for right now, but it's starting at x equals 0, and then it's being moved to the right 3, so that vertical asymptote is shifting right 3 units. Our domain is also based off of this vertical asymptote. So our original log function started off as slowly increasing over time with a domain of x is greater than 0, but as the graph shifts to the right, that graph also moved, and so our domain now is going to be x is strictly greater than 3. Our range, since we have a log function, is all real numbers because this graph continues up as well as continues down. So it goes all the way up to positive infinity, all the way down to negative infinity. In terms of sketching it, we've applied our first transformation. If I were to apply the second transformation, not much would change. This graph would just shift up 5 units, but I would still have the same shape and I would still have the same vertical asymptote here. Let's look at example 2. We have y equals 4 times log base 5 of negative x minus 7. Why don't you guys pause the video and find the parent function. So our parent function for this one will be y equals log base 5 of positive x. So that negative x is not part of our parent function, that's actually a transformation, which leads us to how many transformations do we have for example 2. So in example 2, we actually have 3 different transformations. I want you guys to pause the video here and list all 3 in order in which we would apply them on the graph. So our first transformation is coming from the 4 that's being multiplied out front. That would be a vertical stretch by 4. That negative sign is our next transformation, which is a reflection over the y-axis. And the last transformation we have is the minus 7, which is telling us to shift the graph down 7. So let's graph out our original log function. So we know we have the vertical asymptote starting off at x equals 0. Since the base here is bigger than 1, this is a log graph that would grow over time. When we stretch this graph by 4, that's not changing the vertical asymptote, but it's elongating this curve shape. A reflection over the y-axis will also not change the vertical asymptote, so that's still staying in the same place. But what it will change is our entire shape of our graph. Instead of being on the right side, it's going to flip over, and it's going to be a mirror image. So it's going to be really close down here, and then it's going to get further away over time to be a mirror image of what we had before we reflected it over the y-axis. Then down 7 from here would not change the vertical asymptote either. It would keep that vertical asymptote at the same place, and this graph would just shift down 7 units. Using this information, we can now find our vertical asymptote equation, the domain, and the range. Why don't you guys pause the video and find all 3 of those pieces, and then we'll check it together. So the first thing we're going to check is the vertical asymptote equation, which started off at x equals 0, and even after all 3 of these transformations, it still stayed at x equals 0. The domain, however, started off with x is greater than 0, but because of the reflection over the y-axis, it became x is less than 0. And the range, since we have a log function, started off as all real numbers and will stay as all real numbers, because this graph goes up to positive infinity and down to negative infinity. We have 2 more examples to look at. So let's look at example 3. We have y equals negative log base 10 of x plus 4. Now I know in our last video we talked about if there's no base there, it's assumed to be base 10. So an equivalent problem to this would be y equals negative log of just x plus 4. But I'm putting the base 10 there just to remind you guys that if no base is written, we do assume that it's base 10. But this equivalent problem of just negative log of x plus 4 would be equal to the problem in example 3 as well. Using this information, why don't you guys find the parent function and all of the transformations, and then we'll check that part together. So our parent function for this one will be y equals log base 10 of x, or just log of x, since I don't need to write a base here, and we'll assume the base is 10. Our transformations, we have 2 transformations. The first one is that what's going on with the plus 4, which is shifting the graph to the left 4. And the second transformation is the negative sign, which is a reflection over the x-axis. So if we sketch this original graph, we're starting off with that vertical asymptote still at x equals 0. So this is a graph of our parent function. Because our base here is bigger than 1, we do have the log function that is growing over time. Now let's think about what these 2 transformations would do to this. If we go to the left 4 and then reflect over the x-axis, what do you guys think our final graph will look like? Well, shifting this to the left 4 is going to move that vertical asymptote. So the vertical asymptote will now be at x equals negative 4. The graph will follow along with it, so I'll get this curve. But then, because we're reflecting over the x-axis, I need to flip this graph down, and it's actually going to start up here and get down and decay over time. I'm going to erase that in between one, so, oops, not the whole thing, so that we can see our final graph there. But if it helps, I can do it in another color. We kind of have this in-between graph that came from just shifting it to the left 4, so that's the graph in blue, and then the graph in red where we flipped it over the x-axis is our final graph. Using this information, why don't you guys find the equation for the vertical asymptote, the domain, and the range. So let's check these. Our vertical asymptote we actually already had. That was x equals negative 4, and that came from taking the original x equals 0 and shifting left 4 units. Our domain also moves with that and would be x is greater than negative 4, because the graph, although it is reflected over the x-axis, it's still to the right side of the vertical asymptote, so all of our domain values are still bigger than that vertical asymptote, so x is greater than negative 4, and our range is still going to be all real numbers. We have one more example to look at, and in this example, we're going to notice that our base now is actually going to be equivalent to an exponential decay graph if we were to look at the inverse, just so we get a sense of what that graph would look like as well. So here we have y equals log base 1/3 of x minus 1 minus 2. Why don't you guys pause the video here and find your parent function and find all of your transformations. So for our parent function, we just get y equals log base 1/3. Seems a little funky, but it does work to have a fraction as our base. So we get log base 1/3 of just x. We have two transformations here. The first transformation is coming from the -1, which is telling us to go right 1. And then the second one is coming from the -2, which, since it's outside, is telling us to go down 2 then. Our original graph here is going to look a little bit different to start off with, because our base here, which is 1/3, is less than 1. So I still have the same vertical asymptote, but instead of it starting down here and growing over time, because our base is less than 1, it's actually starting up and then getting smaller over time. From here, why don't you guys determine what our final graph would look like if we were to sketch that out using the right 1 and the down 2 as our two transformations. So to check that graph, if we shift this to the right one, the vertical asymptote is going to move 1 unit to the right, and that will end up at x equals 1. The graph would still look the same, just moved over right 1. And then if I shift down 2, it slightly shifts it down 2, but I get pretty much the exact same graph. Using this, why don't you guys find our vertical asymptote, the domain, and the range. So our vertical asymptote is at x equals 1, since we shifted to the right one. The domain is going to be at x is bigger than 1, since the entire graph is still to the right side of the vertical asymptote. And our range is going to be all real numbers. So in this video, we saw the connection between an exponential graph and inverting it to get our logarithmic graph. We also talked about how the transformations can be applied to our log graphs as well. We talked about how the domain and the range could change, as well as the vertical asymptote from there.